I welcome all of you to the class. As far as the today's class is concerned, in today's class we'll be talking about few problems that we need to solve with the help of Clayperons three-moment equation. Okay, so the subject is about, or today's lesson will be about application of. We'll be trying to apply application of Clayperons three-moment equation. Now, Clayperons three-moment equation says MA into L1 plus twice MB, L1 plus L2 plus MC into L2 is equal minus 6 times A1 X1 bar by L1 plus A2 X2 bar divided by L2. Fine. Let's take a beam. We have a beam. Let me write over here. This beam is given that it's simply supported at end A. It is simply supported at end C. It is simply supported at end B. It is subjected to a uniformly distributed load over it. Okay. It is subjected to a uniformly distributed load. This length is given to us as, sorry. This is given to us as L1. This is given to us as L2. Fine. So let me mark it. This is uniformly distributed load. Its intensity is W, kilonewton per meter. This length is L. This length is also L. So we are having reaction here. We call that as RA. We have a reaction here. We call that as RB. We are having reaction here. We call that as RC. This is A. This is B. And this is C. Okay. So it's also given that the beam is simply supported at A and C. When the beam is simply supported at A and C, that means MA is equal to 0 and MC is also equal to 0, because this is given to us that the beam is simply supported at C. We are also given that L1 is equal to L2 is equal to L. Fine. What is this A1? A1 is the area of the moment diagram, free moment diagram for the section AB. A2 is the area under the moment diagram for the section BC. So let's draw the moment diagram. Free moment diagram. How do we draw the free moment diagram? It's quite conceptual in the sense that first of all, we'll take the section AB. Okay. Once we take the section AB is having length L. We assume that this beam is, or this section is simply supported at A and B, and it is subject to a uniformly distributed load. Therefore, it will be having what we call as a hyperbolic curve. This is the free bending moment diagram for a simply supported beam having uniformly distributed load over it, such that the maximum moment will be equal W L square divided by 8, and its centroid is here at a distance L by 2 from the left hand. Okay. Same will be the case for the right section, such that this is equal WL square divided by 8, and the distance of the centroid from the left hand is equal to L by 2. Right? This is the free moment diagram. Then what we also draw, we draw what's also known as their fixed moment diagram. We assume that the moment at A is having some value, moment at B is having some value, moment at C is having some value. Since we are given that the beam is simply supported at A and C, that is moment at A is 0, moment at C is 0, but moment at B is not equal to 0. It will have some value. Okay. Therefore, join these two lines, join this point with this point. Okay. So this area that lies between this red and black, this area, this area, this area, and this area, this represents the exact bending moment diagram for this type of beam. Anyways, let's first of all concentrate over here. So we can write this as this is 2 times MB. L1 is equal to L2 is equal to L. So this is L1 plus L2 will be 2 times L, will be equal minus 6 times A1, area of this hyperbola, that's equal 2/3 of its length, that is 2/3 of L, into its perpendicular maximum value, that is W, L square divided by 8. Fine. And you have your x1, that is x1 is equal L by 2. And in the denominator, we are also having L1, that's equal L. So let me write that as 2/3 of, let me write it here. Plus, again, A1 is equal to A2, x1 bar x2. So we can also write this as, this entire term is plus 2/3 of L into L into WL square by 8 into L by 2. That is 4 times MB into L is equal to minus 6 times. That is L and L will cancel. This is WL cube. So it is this term and this term are same. So I can write this as this is 2 times W L cube divided by 24. So that will be minus WL cube divided by 2. So MB will become equal minus WL square divided by 8. This is the value of MB. Okay. Now do one thing. Take a section of this beam at point B and say shear force there is V and bending moment there is, there the bending moment is now equal to MB. Okay. So summation of all the moments about point B has to be equal minus WL square divided by 8. So once we take a section here, we'll take the left moments into consideration. So it will be RA into L, that is clockwise, we'll take it minus plus WL into L by 2 is equal to minus WL square divided by 8. So RA into L but minus is equal minus WL square by 8 minus WL square by 2. That's equal to WL square minus WL square prime into minus WL square. Sorry, it will be WL square by 8. And we're also having minus WL square. So it will be minus 5 by 8 WL square. Okay, W into L. Fine. So this is a correction here. This is equal W into L. So this is minus 5 by 8 WL square. That's equal minus RA into L. L and 1 will square will cancel. So we can at least say that, let me write it over here, that the reaction RA is equal to minus 5 by 8 W into L. Sorry, it will be plus. Okay. So this is the reaction at A we have obtained. Now we have to obtain the reaction at C. How we'll do? We'll take this next section of the beam into consideration and again take the moments about point B. Therefore, we will have, when we take the next section into consideration, we'll be having the moment because of, now see, when we took left section into consideration, at the time we said MB is equal to how much? Minus WL square by 8. Once we take the right section into consideration, the moment there will be negative of the moment. That's on the left hand side. Or let's see, that is minus WL square by 8. So this is RC into L is because of RC, anti-clockwise moment, positive, minus WL into L by 2 is the clockwise moment. Okay, that's why negative is equal to minus WL square by 2. So once we solve it, we'll again get RC will also be equal to 5 by 8 W into L. Okay, so RA, so here we can at least obtain the information that RA is equal to RC. Now we have RA plus RB plus RC is equal to the total load acting on the beam, that is 2 times W into L. This is W into 2L actually. So we know the value of RA, that is 5 by 8 WL. We know the value of RC, that is 5 by 8 WL. Okay, that's equal 2 times WL. Therefore, from here we can get the value of RB. RB will be equal 2 times WL minus 5 by 4 WL. Okay, so from here we can get the value of RB will be equal 3 by 4 W into L. So we have obtained the value of RA, we have obtained the value of RB, we have obtained the value of RC. This is how we go ahead with the help of, we use this 3-moment equation for solving the continuous beams and obtaining the reactions and the bending moments. We'll continue with more examples in the next class. Thank you.